Okay, this is a tutorial on thin layer and column chromatography of organic compounds. And so first we should define what chromatography is. Any type of chromatography, and there are many that you'll learn about in organic chemistry, involves separation of organic compounds in a mixture. And there's two important concepts that you have to understand the process of chromatography. And the first is that you have a stationary phase that doesn't move and a mobile phase that does. And it's the partitioning of the component between sticking to the stationary phase and being dissolved in the mobile phase that causes the separation. And if two different components have two different abilities to partition between the stationary and the mobile phase, that's where you get the separation of the components from in chromatography. And that'll become a little bit clearer as we go through the basic concepts. So what we're going to do in this experiment is we're going to do thin layer chromatography and column chromatography. So the first step is we place a sample mixture and we adsorb that onto the stationary phase. Now notice this is adsorb with a D, which means that it basically is adhered to the surface. Something that absorbs goes deeper into the material. So we're just adsorbing it onto the surface. So that occurs by intermolecular forces. For instance, if you've done paper chromatography in the past, or if you've done like t-shirt chromatography, then what you do is you take a filter paper or a piece of cotton, and that's your stationary phase. Either of those would have cellulose as their basically chemical structure. Here's sort of the structure of cellulose. It's a series of sugar molecules, and it's got lots of OHs in it, so it's a polar stationary phase. That's its polarity. So the surface of the paper would have hydroxyl groups, and probably attached to those hydroxyl groups would be water molecules that may be adsorbed onto that surface. Therefore, that makes this a polar stationary phase. In thin layer chromatography, what we have is we have a thin layer of silicon dioxide that gets coated onto a piece of glass or plastic. We're using plastic TLC plates because they're easy to cut with a pair of scissors. But sometimes in research we might use glass ones where there are pieces of glass coated with the silica gel. Those are a little bit more difficult to cut. So we have silicon dioxide on the surface of the glass or the plastic, and then unless we dry our plates, there's always a layer of water that's adsorbed onto that silica. So we have a polar stationary phase because we have OH groups then on the surface of the TLC plate. And these are typically the types of TLC plates that we use in organic lab, will be those that have the polar silica gel. Now it is possible sometimes to coat a plate with something that's non-polar. This slide says like mineral oil. There are better things to actually coat the plate with. If you know what the product Rain-X is something that you put on your windows of your car and it basically waxes them. If you took a TLC plate and you coated it with Rain-X, you would actually adsorb and hopefully chemically connect a non-polar material to the surface of that plate. When you use a non-polar material on your TLC plate, that actually becomes what we call reverse chromatography. And there are times when we actually want to do this because we want to adsorb our non-polar material, and we'd actually like to use water as our solvent. But normally, with a polar stationary phase, we're using relatively non-polar solvents, not water. So we're not going to do reverse chromatography, but it is done in certain applications, including environmental chemistry. So what we do is we put a spot of our mixture onto the TLC plate or the piece of paper. And so it adsorbs on there by forming having intermolecular forces. Then we take that stationary phase, that TLC plate, and we put it inside of a beaker, or in our case a TLC jar, where we add solvent to that TLC plate, or the solvent has already been added. That's going to be the mobile phase. And so the mobile phase will move up the TLC plate during the experiment. And we normally cover this to keep the vapors in, because what we don't want is we don't want the solvent to move up the TLC plate and then evaporate. So we have to close the jar up in order to keep the solvents from evaporating. And so this is sort of like sticking a piece of paper towel into a beaker containing water. The water will move up the paper towel, it'll move up the silica gel TLC plate. And so as that solvent then moves up the TLC plate, the components of the mixture will also either move with the solvent or they'll stay stuck to the stationary phase. And each compound is going to partition between dissolving in the mobile phase or staying adsorbed onto the stationary phase. And at the end of the experiment, what we'll have is the solvent will have moved so far up the plate. Usually we let it run about 3/4 of the way up the plate, and then we'll end up with a spot where the mixture, where the component has moved in the mixture. And then we have the initial spot where it was at. Okay, and this is what's called development. So when we develop a TLC plate, that means we put a spot of the mixture on there, we place it inside of the development jar, and then we go ahead and allow the mobile phase to move up the TLC plate. That's development. So let's look at a little bit more detail here about how the materials separate in a TLC experiment. So again, we put our mixture onto the surface of the plate, and then we stick the plate into the mobile phase. Now the compound is physically adsorbed onto the surface of the plate by some type of intermolecular force. If it has OH groups, it might hydrogen bond. If it has other polar groups, it might accept the hydrogen bond from the water. If it's just a non-polar material, then it'll have like a dispersion dipole interaction. But somehow it's physically adsorbed onto the surface, like this molecule here. So I'm looking at this sideways. So when I put my plate into the bottom of the beaker is over here, and the solvent is going to move this way. Okay, so as that solvent moves, then there's going to be an equilibrium between the component being adsorbed onto the stationary phase and it being dissolved in the mobile phase. And so when it dissolves in the mobile phase, it will then move with the mobile phase. So the equilibrium here is either being in the mobile phase or being adsorbed onto the surface. Okay, and so when it's dissolved in the mobile phase, it will move up the plate. When it's adsorbed onto the surface, it won't. It's stuck. And so it's this equilibrium, or what we call partitioning, between the mobile phase and the stationary phase that will cause the material to move up the plate. How much will it move up the plate? Well, that's going to depend on the relative strengths of its intermolecular forces with the polar plate or its intermolecular forces with the mobile phase, which is typically non-polar. We have to have some contrast between the polarity of the phases. So the mobile phase is typically less polar than the polar stationary phase. So the dissolving adsorption process occurs thousands of times as this material moves up the plate. And so if each component then partitions itself between the stationary phase and the mobile phase differently because it has a slightly different polarity and therefore slightly different intermolecular forces, then what happens is over the course of this equilibrium, the components will stay stuck to the stationary phase a different amount of time. They'll be dissolved in the mobile phase a different amount of time, and therefore they will move at different rates up the TLC plate. So this is based on polarity, this separation, and that partition between sticking to the plate or dissolving in the mobile phase. Now I should stop here for a minute and say that the TLC plates that we develop look an awful lot like what you do in biology for gel electrophoresis. And there's probably similarities between those two techniques. But the one thing that people have difficulty sometimes in differentiating between the two techniques is this. In biology, when you do gel electrophoresis, you're separating the components based upon their molecular weight. In chemistry and organic chemistry, we're separating these components based on polarity, not molecular weight. So you have to keep those two techniques straight in your head. Polarity in organic and molecular weight when you're doing gel electrophoresis. So the components will essentially move up the plates at different rates depending on their polarity and how much time they spend dissolved versus how much time they spend stuck to the plate. So what we'll do for TLC is we'll place a spot of that component onto a TLC plate, we'll develop it, and if we see multiple spots, then we know the sample wasn't pure, it had a mixture. If we see a single spot, then a couple of things could be the case. If we see a single spot, it could be that our solvent wasn't good enough to differentiate between multiple components. Or sometimes if we just have a single spot, we might want to look how far it moved up the plate as sort of a screen for its identity. One of the simplest tests you can do in forensic chemistry is to take and put a spot of an unknown material and put another spot of a known material onto a TLC plate and develop them. If the two spots move exactly the same distance up the TLC plate, then that says that the unknown might be the known compound. So if I had some illicit drug sample or I thought it was an illicit drug, I might put a spot of that against some known drug. And if they move the same amount, then it would tell me, well, this could be that illicit drug. Now, it's not a positive confirmation. If the two had completely different, moved completely different distances, then that would rule out that as a potential illicit drug. And so TLC is used a lot as a very simple test in forensics. It's not a test that will positively identify, but it actually will positively disqualify different things if you do a quick TLC and they don't match up. If they do match up, then it means you need to investigate further. In this class, we're going to use it that way, but we're also going to use it to determine purities, because if we see more than one spot, that means our sample is impure. Okay. So in terms of looking at the TLC plate, there is a way to quantitatively measure how much time the spot spent stuck to the stationary phase versus how much time it spent in the mobile phase. And this is what's called the RF value. And the RF value is simply the ratio of the distance that the compound traveled over the distance that the solvent traveled during the development. And we usually measure this with a ruler. Typically you'll measure center dot, start to center of the dot, and then the solvent line you mark. As you pull the TLC plate out of the developing jar, you immediately mark how far that sample or how far the solvent moved up. And we make all of our markings on TLC plates in pencil. Because if you use pen inks will chromatograph. They'll chromatograph just like the spots of our sample, and so we don't want to contaminate it. So we always use pencil to make our markings. So that's the RF value, the distance that the spot traveled over the total distance that the solvent traveled. And that's going to be a ratio then, a ratio between 0 and 1. If the spot spent no time on the stationary phase and was totally dissolved in the mobile phase the entire time, you're going to get an RF value of 1. If it stuck to the plate, never dissolved, then you're going to get an RF value of 0. And typically we'll have RF values between 0.1 and 0.9 because we want the solvent to dissolve the material some of the time, but you want a good partition between the two phases in order to get good separation of your different components. Okay, so that's our TLC, and you'll see more examples, or already have seen more examples of the TLC with the spinach pigments that's in the other lecture video. But let's say that I determine that I have more than one component in my mixture and I wanted to separate them. Well, TLC is not the best method of separation. It can be done. You can actually develop the TLC and actually take a razor blade and cut the silica gel of this spot out and then redissolve your material into a solvent in order to basically separate one component from another. That's pretty extreme. What we really need is sort of a three-dimensional plate that allows us to separate the components and then collect each component one at a time. And so that's what column chromatography is about. In column chromatography, I'm going to take a column of that stationary phase. Usually it's the same silica gel that we use for our TLC plates, and I'm going to pass the material through that column of the stationary phase, and then hopefully the components separate, and then they come out the bottom of the column one by one so I can place them in test tubes. The kind of column chromatography that we're going to do for the spinach pigments is we're going to take a small glass Pasteur pipette, put a little piece of cotton down at the bottom, and then use 1 inch to 1.5 inches of aluminum oxide as our stationary phase. Okay. In the later experiment, we're going to do this on a bigger scale and a much more tedious process where we separate the components of an Excedrin tablet using a larger column and doing it typically like we would in a research situation. But in this experiment, we're just going to do a small column, and our goal is going to be to separate the nonpolar keratines from the polar chlorophylls, the two main pigments in spinach. We're going to have no control over here, so the solvent's going to constantly be dripping out. And sometimes we have a stopcock here that allows us to stop the flow, but we're not going to actually have that in either of the column experiments that we do in this semester. So we take a Pasteur pipette, we make a column of aluminum oxide, we basically we first of all have to wet the column. So we typically use our chromatography solvent. We pass pure chromatography solvent through the column so that the column becomes wet. If you place the solid material in here and then add liquid to it, that's called dry packing the column. That's what we're going to do in this experiment. Later on, we'll use a slurry of that solvent stationary phase mixture to do what's called wet packing the column. But today we're going to dry pack it. So after we have added pure chromatography solvent to the column, we then place the mixture at the top. And so the mobile phase will be added to the top of the column as well. Gravity will cause the mobile phase to move through the column from top to bottom. And as the solvent moves down the column, the compounds will hopefully separate on the stationary phase by the same process they did in the TLC plate, by the process of adsorbing versus dissolving. And so what will happen is at some point we'll have different components at different places on the column, and as they elute off the column, we'll be able to collect them in separate containers. So for instance, if component A comes off first, we'll collect it in one container, then compound B will come off, and then compound C, and then finally compound D. So if we do this right, if we choose the right solvent that separates the components, what we can do is if we collect small, what are called fractions, then we'll basically separate the components, and we'll have maybe, we use disposable test tubes in this lab, we'll have little disposable test tubes that contain pure component B or pure component C. So that's how we would work with the column chromatography experiment. So TLC is used to judge the purity of the compounds and sometimes make identities. Column chromatography is what we use to actually physically separate the components of a mixture by, again, passing that mixture through a stationary phase and having it separate. And then as each component elutes off the column, and that's the term we use is elute, then we can put it into its own separate container. This is sometimes a very tedious process, but it is a fairly effective one to purify and separate components of a mixture. So that's what we're going to do in this experiment. Remember, it's the polarity difference between the stationary phase, the mobile phase, and the amount of time that the compound is partitioned between being stuck to the stationary phase and dissolving in the mobile phase that causes the components to move up the plate, or in this case down the column. And hopefully if the compounds have different polarities or slightly different polarities, they will separate from each other as they either move up the TLC plate or in this case down the column. Okay, so this is the basic technique or theory behind column and thin layer chromatography.